Hello, good morning, afternoon, evening, good night, wherever you are, everyone. Welcome at the session, which will be about 8 short papers. It's a very packed but very exciting program. The topic of this session is rendering images and application. And we are having papers from both computer graphics and visualization. So I think it's a very nice mixture of different and diverse topics. And without any delay, because we are heavily packed in this session, we start with the first presentation. The presenter will be Wenkai Han. Very welcome. And the topic of the paper is sketchy rendering to aid the recollection of regular visualizations.
Hi everyone, I'm Wenkai Han from the Department of Computer Science at Aarhus University. And today I have the pleasure to present our short paper in Eurovis, Sketchy Rendering to Aid the Recollection of Regular Visualizations, in collaboration with Michael Larsen and Hans Jorg. Our paper aims to address one unique problem in some visualizations with very regular appearances, like matrices or unit tree maps. They have a grid-like look and feel that makes it very hard to orient oneself on the displacement of the paper in Eurovis, Sketchy Rendering to Aid the Recollection of Regular Visualizations, in collaboration with Michael Larsen and Hans Jorg. Our paper aims to address one unique problem in some visualizations with very regular appearances, like matrices or unit tree maps. They have a grid-like look and feel that makes it very hard to orient oneself on a large scale and equally challenging to discern one metric cell from another on the detailed scale. The most common way to counter the uniform appearance of these visualizations is to use some form of coloring or shading of the individual elements. For example, using a stripe pattern like the graph on the left and the center, or multi-hue color mapping like the graph on the right. However, as color usually has been already used in visualizations to encode data, in this paper, we propose using a different approach, sketchiness, to help orienting users. Using sketchiness in data visualization has been explored with the emphasis on mimicking human drawing imperfections, which works reasonably well for indicating uncertainties in data, like the two graphs on the top. It had also been extended to some 3D applications. In this paper, we have a different goal, using sketchiness to enhance visualizations that have a very regular appearance so as to improve the discernibility and memorability of the individual visual elements. Now, we choose sketchy lines over fill colors for several reasons. First, as we mentioned before, color has been very commonly used in visualizations to encode data, but sketchiness as a channel is in most cases still available. Second, compared to colors, sketchiness is perceived primarily as a visual style, not so much as carrying actual meanings, so it is less prone to be misinterpreted. Moreover, sketchy lines only perturb the gridded outline of the visualization layout, therefore it leaves the interior of the visual elements available for showing additional data attributes. Previous research on using sketchiness primarily focused on imitating hand-drawn lines to generate a more realistic feeling. However, our goal is different, to generate distinctive-looking line styles for visualization grids so it's easier for users to navigate themselves. And that's why we introduced several parameters to increase the diversity and distinctiveness of the visualizations. Here you can see an example of a sketchy line and its parameters, and we'll go through the parameters individually to see what each parameter does compared to the base scenario. First, P stands for the number of control points. The more control points one uses, the more deviations from a straight line will appear. Next, A stands for the amount of displacement on each control point. This amount captures how far from the straight line a control point can be placed, which is randomly chosen from an interval of A. Here we can see when the interval of A increased from 10 to 18, the displacement of sketchiness also increased. D stands for the distribution of control points along the line. Here we use the base distribution, where when D equals to 1, it yields a uniform distribution, and when D is higher or equals to 2, it yields a probability distribution skewed towards the center of the line. And when D equals to a negative number, we compute the inverse of the base distribution to generate a skew towards the endpoint of the line. And O stands for the order in which the control points are connected. We specify the order as a list of offsets in which the points are used. For example, a single element in the list +1 generates a simple sequential order, and +3 -1 connects the points in an order of an overjoined line in a back and forth style with 3 control points up and 1 control point back iteratively. Finally, the two sets of parameters SW and SC define the stroke width and how it changes. SW is an interval of stroke width to be used, and SC is the count of points for which a stroke retains its width. For example, here we can see that the stroke width can vary from 2 to 8, and it will change every third control point. After generating the sketchy lines, we will need to assemble them into sketchy shapes. To draw shapes using our sketchy lines, we have in principle two fundamental options. Keep the line disjoint with several strokes, or concatenate the lines into a path in a single stroke movement. Thereafter, we generated 2D Perlin noise fields, one for each of our 4 parameters we vary, to assemble the sketchy shapes into distinctive-looking grids. 2D polynomials allow us to generate a random-looking grid with some continuous local attributes as regional anchors for users. Drawing inspirations from the previous 2 styles of sketchy shapes, we propose 2 different approaches. For the line-based approach, we piece together the grid from individual sketchy lines, and for the shape-based approach, each square is drawn with a single movement, then pieced together into a grid. To validate our design, we conducted a lab study to test our hypothesis that with sketchy grids, the time and error will be lower for the recollection of a data point in a regular visualization. The main procedure of our evaluation is as following. A matrix will appear for 5 seconds for the user to memorize the location of a randomly generated highlighted cell. After 5 seconds, the participants will be distracted by a simple 2x1 multiplication problem. Then they will be asked to relocate the previously highlighted cell. Here is an example of the 3 grids that we used. Each participant will have a set of 3 randomly generated grids, and 16 participants finished the evaluation. Note that we did not explicitly ask them to use the sketchiness as a reference to locate the target points during the evaluation. This would help us to understand how users might react and perform in a natural setting. Among the 16 participants, 6 participants reported to have used the sketchiness as a reference for relocation intentionally and consciously. For them, we found that their response time with line-based sketchy grids was significantly better than with both straight line and shape-based grids. This also corresponds to what participants reported in the post-study interviews. Some participants stated that the line-based approach would generate more distinctive-looking local areas that would help them as additional anchors to relocate the previously highlighted cells. This brings us to the conclusion of our study. Sketchiness has been used in the past mainly to communicate levels of uncertainties. In this paper, we looked at a different possibility, using sketchy rendering to create more distinctive grid drawings. Through a small lab study, we gained partial confirmation for our intuition that the sketchy visual features could provide additional cues for orienting in a very homogeneous visualization. We can easily envision this idea being applied beyond the realm of matrices and tree maps. For example, a packed bubble chart could benefit from a similar sketchy treatment. This brings us to the end of our presentation. Thank you for your time, and feel free to dive in the detailed user study data and the prototypes through this link.
Great. Thank you,
Yes.
Wenkai. It was a very nice presentation.
Thank you.
And it's time for questions. And I still don't see any from the audience. I think they're still warming up. So I have mine, of course.
Yeah, go ahead.
I actually really admire how you are changing this. It's something which is close to my heart. I really enjoyed some like distortions in the regularity in the representations. My question would be about what's your opinion on if you are introducing this random thickness of the individual parts in your representation? Did the participants or you have some thoughts, comments on if it somehow visually navigates the user to some parts which are look like more important from this point of view because it's thicker there, or is it something which you don't think is a problem in this?
So from the user study, there are one or two participants reported that it might be a bit annoying in the beginning to see a sketchy background, but over time they got used to it. And since the sketchiness is somewhat random, I didn't have any participants reported that the sketchiness make them or kind of subconsciously force them to focus on any point. So we didn't see that from the user study, but I can see that that might be a concern. And if you do more user study in more different scenarios, you might see more different insights on this. But
yeah, it would be really nice to see some application on different types of grids and so on as well. I think just go on, it's really nice work.
yeah, I think it's very interesting, and also how this bring a very different way of showing the background and orienting people. So yeah.
Definitely. Okay, so I don't see any other questions, just clapping and waving. So everyone is greeting you.
Yes.
And because we are really packed in time, I have to thank you for a very nice presentation once again, for your answer to my question. And just go on, and we will continue with the next talk.
All right. Yeah. If you have any further problem, you can go to the Discord and we can discuss further. Yeah. All right.
Perfect. Yeah. Let's meet at Discord channel afterwards. Thank you. Thanks a lot. So we are slowly continuing to the next talk, which will be given by Cynthia Tian, and it will be about progressive rendering of transparent integral surfaces.
Hello everyone, thank you very much for coming to the presentation. We are Tobias and Xingze from ETH Zurich. Today we are going to talk about our short paper on progressive rendering of transparent integral surfaces. Geometry-based flow visualization methods such as stringline and pathline rendering are among the most commonly used visualization tools. By extending a seed point to a seeding curve, integral surfaces arise, which convey shape information better than lines. Theoretically, an integral surface can be considered as the collection of infinitely many integral lines from a continuous seeding curve. In practice, we usually generate discrete samples on the seeding curve, advect an active particle front through the domain, and tessellate between the front lines. This, however, can be problematic due to the triangulation process. Since the distance between neighboring frontline particles may grow or shrink, the front line has to be refined adaptively. As illustrated here, particles can get stuck at boundaries, obstacles, or critical points, resulting in an infinite amount of refinement. Further, if the surface passes through a shear flow, the triangles degenerate. Much research has been done to handle these cases. However, they all need to refine either front lines or the entire surfaces, which requires heuristics in situations when the refinement becomes unbound. Mahado proposed an image space string surface rendering method that progressively renders many string lines into the back buffer. Their basic idea is to render many lines to form a surface to avoid triangulation. They first sampled the seeding curve with respect to a physical space threshold and traced the particles. At each time step, they performed resampling on the front line. When two consecutive particles are further away from each other than an image space threshold, they inserted new particles in between. This ensures that there are as few gaps as possible in the final image. As they use the depth buffer to determine the fragment order, their approach is limited to opaque surfaces. However, transparency plays an important role in scientific visualization. As we can see from the examples, transparency helps to reveal more inner structures of the data. In this paper, we extend Mahado's work to enable transparency. we propose a new GPU-based progressive rendering algorithm that renders many integral lines to form transparent integral surfaces. For this, we implemented a pixel-based tree data structure to keep track of the progressively rendered transparent layers. We provide an interactive framework for users to explore various flows and parameters. The rendering of transparent surface geometry requires an order-dependent compositing. This is either done through multi-pass rendering methods or by storing and sorting all fragments. In a progressive renderer such as ours, more and more fragments are rasterized over time, ultimately sampling the surfaces densely with an unbound number of transparent fragments. Storing all samples is infeasible. Various approximations have been proposed to composite the layers ordered independently by using a weighted average or weighted sum. These formulas would converge to opaque surfaces when n reaches infinity. In multi-layer methods, the variable sampling density will cause biases in the bins when the surface layers in a bin were sampled at different rates. Due to the small variations in depth values of the line geometry, it is difficult to get accurate line counters along the viewing ray, making transmittance approximations infeasible. All of the existing methods are not suitable in a progressive situation. We propose a new method to render transparency progressively. Every frame will only render a limited amount of lines and hence have fixed memory consumption. The algorithm can be divided into 3 steps. First, we rasterize the line geometry and construct unsorted fragment length list. Next, we add each fragment to a per pixel tree data structure. In the end, we composite the tree nodes to get the final image. Our algorithm starts with sampling a set of integral lines from the seeding curve. The easiest way is to sample uniformly with the Hutton sequence. This results in deterministic samples with low discrepancy. A simple Hutton sequence was sufficient for our application, though the use of other adaptive sampling strategies would be imaginable as well. We trace curves from the samples using 4th Range-Buta integrator and compute normals using ghost particles. The lines are rasterized and we then create an unsorted fragment linked list for the line geometry. To blend the line fragments properly, we construct a per pixel tree structure. For each fragment in the linked list, we traverse the tree based on the depth of the fragment. When a fragment has a smaller depth value than the tree node, we go left. Otherwise, we go right. When a fragment is close enough to a tree node, we merge the fragment into the tree. After inserting the fragment linked list into the tree, we render the tree with a front-to-back scheme. Our tree is naturally sorted by depth, and hence we simply blend from the leftmost node until we have visited all the nodes in the structure. We apply our algorithm to both analytic and numerical flows. In analytic flows like ABC flows, the domain is filled with separating structures that prompt the front line to expand and refine in a space-filling manner. Since we do not need to refine the front line, our surface is without artifacts. Our algorithm is able to generate transparent surfaces even in very complicated and turbulent flows without the flaws arising from triangulation. In this video, we rendered 100 lines per frame. Our algorithm ensures transparent intermediate results as preview at every step. Users can interactively explore the flow or analyze the results on the fly. We also test the time taken for each individual pipeline step for all the datasets used in this paper. When rendering 10 lines per frame, the composition step takes the longest time. Does that mean this step is a bottleneck of the algorithm? The time needed for this step is actually fixed for all the sample sizes once the per pixel tree is converged. We show the memory consumption of our per pixel tree over time. As the number of tree nodes converges, the memory required also converges to a constant, which is the upper bound for each scene configuration and is dependent on the depth complexity of the current view. As the node memory pool is shared among pixels, the time to perform the blending of the transparent surfaces also converges. Our algorithm still has some limitations. We traced the integral curves on the CPU on a single machine. Our CPU implementation is a proof of concept mainly suited for the rendering of still images. Interactive rendering of closed surfaces would require GPU tracing and adaptive seeding. Due to the view dependence, the memory consumption can be small even for potentially large scenes. However, the data structures are rebuilt when the camera moves. Reprojection methods for real-time rendering could be used to reuse screen space information from a previous frame. That's the end of the presentation. Thank you very much.
Perfect, Xinjie. I think we are connected now. Thanks a lot for a very nice presentation and impressive work. I'm checking if we are having some questions from the audience, but looks like for the WIS community, it's quite tough topic to, to have some meaningful questions, but maybe they will still come. Meanwhile, I want to clarify a bit or catch up on with what you were mentioning at the very end of the presentation, and it's about like the extendability of your algorithm for dynamic scenes, because there was like slight mention of that. So could you comment a bit on that, how this could be easy to do or complicated?
Because currently we only trace on the CPU, because for this project we only do that for simplicity. It is imaginable that if we move the tracing part to GPU, the performance would be much better, and it means you can render many more lines, so your surfaces can converge very quickly. So that in dynamic situations, it means like you instantly get a converged surface at each frame. So then you have a dynamic scene. But currently, because it takes some time for our surface to completely converge, so yeah. So it's a bit difficult to get really dynamic results.
Yeah. Looks like your next full paper, right? Let me check. There's nothing still yet. So maybe one small question. The next one, just to clarify, maybe I just really misunderstood. If you were when you were showing the results in your video, when you were rotating the scene and playing with the scene, then within the zooming, you also had to recalculate everything. So is it something which has to be done like every time, or can we use the information that the scene is viewed from the same viewport, or?
Because currently we construct a per pixel tree, so that means we only blend the tree information, not at like all of the data. So currently it's like very view dependent. In the future, we are thinking maybe we can add some projection methods, so we can reuse the trees constructed in the previous frame and reproject it to the next view. But currently we still need to reconstruct the tree, because every time you change this, the depth distribution will change. So that means the tree needs to be recreated.
Okay, perfect. Thank you very much. And we need to use the opportunity to have a question from the audience, because we have one. So okay. I won't let you out still. We have questions from Andreas Vasilakis, who is asking why the final stage, composition, takes so much time.
That is actually the time that. So basically, we only record the time when the tree is completely converged. So we don't show intermediate results. So initially, you would only have a few nodes per pixel. So that would converge very that doesn't take much time to composite. But when the surface converges, that means you would have so many lines and to create a surface without a gap. So that means you actually have a lot of tree nodes for each pixel, and it would take some time to composite. But we find that for one scene, once the tree is converged, this composition time is actually a constant, so it won't go unbound.
Perfect. Thank you very much. Thanks a lot for all your answers. Thanks a lot for a very nice presentation and good luck with your ongoing work. It's really very nice. Looking
Thank
forward
you.
for the results.
Okay.
And let's switch to the next talk, which will be done by Carlos Andujar. And the topic of the talk will be effective visualization of sparse image-to-image correspondences. So let's have a look on this presentation now.
Carlos Andujar from UPC in Barcelona. During the next 80 minutes, I will be presenting our paper on visualizing image correspondences. This is a joint work with Marco Mino and Antoni Chica, also from UPC. So let me start with an overview. Finding correspondences between images is a crucial step in many computer vision applications. The traditional approach is to place the images side to side and draw segments connecting matching pixels. In this paper, we present a new visualization technique that features the clustering of consistent matches, the optimization of the image layout to minimize occlusion, a color mapping to minimize color interferences, the bending of link segments to put apart nearby links, and the use of glyphs to facilitate the identification of matches. As you can see, our technique substantially reduces the clutter and thus makes it easier to detect and inspect matches. Here is an outline for the rest of the talk. Establishing correspondences between images is an essential step in a number of applications. The standard approach is to first process each image to detect key points, which are represented with a descriptor, and then images are processed in pairs, and key point descriptors are compared to find correspondences. Although these descriptors have been designed to handle some image differences, for example, viewpoint changes and intensity variations, large differences often cause wrong matches. Major challenges are occluding objects, mirror-like surfaces, and self-similar structures. The input of our algorithm is a collection of matches, where each match is described as the key point location on one image and the matching location on the other image. And the output is a composite image that should facilitate two user tasks. First, users should be able to identify individual matches and given an arbitrary point on one image, finding the matching key point on the other image. And second, users should be able to see the image contents under each key point. This means that visual overlays should occlude as less as possible. Traditionally, these matches are shown by placing the two images side to side and drawing all link segments. But this approach tends to produce cluttered images, where individual matches are hard to identify and the underlying image is hardly visible. Another option would be to select a random subset of the matches, but of course we would lose a lot of information. So our problem can be seen as a particular case of graph visualization. However, most graph layout methods are concerned with the placement of graph nodes, which in our case are fixed. Edge bundling methods merge geometrically close edges to reduce clutter, but bundles could result in ambiguity unless only edges with both a common origin and a common destination are bundled. And finally, origin-destination flow maps address a similar problem, but in our case, origin and destination locations are densely spread across the image and the flow is constant. So let's describe our approach. A first idea is to use hierarchical clustering to group consistent matches. The clustering algorithm proceeds bottom-up by iteratively merging clusters. We need to decide two things: how to measure the distance between matches and the distance between clusters. For matches, we just use the distance between the points in four-dimensional space. So we cluster edges with both endpoints at nearby locations. And for clusters, we explore three metrics using the minimum, the average, or the maximum distance between a match in one cluster and a match in the other cluster. This figure shows the output for these three strategies in a typical case. The mean metric, also known as single linkage, tends to generate large clusters representing inlier matches and keeps isolated matches in their own clusters. This metric is suitable when the major task is the inspection of potential outliers. In contrast, the max metric, also known as complete linkage, keeps clusters from growing too much in extent. And for a fixed number of clusters, this means that outlier matches are likely to be merged into other clusters, and those fade out in the final image. This metric is mostly suitable when we wish to neglect outliers. And the average matrix provides a trade-off between inlier and outlier attention. Another idea is to optimize the layout of the images to minimize the occlusion caused by the edges. We find the translation vector that minimizes the sum of square edge lengths, subject to the constraint that the translated images do not overlap. This figure shows the optimal layout for different image pairs. Using different colors makes it easier to follow the segments. We use Kelly's palette, which contains 22 colors of maximum contrast. We exploit the fact that all segments must go from one image to the other, and those must cross a shared axis. We thus compute the intersection of all segments with that axis and sort them according to their intersection point. Finally, we use this rank order to assign palette colors to segments. This figure compares different color mappings. Our strategy succeeds in assigning different colors to roughly parallel segments. Some nearly parallel segments still might be hard to follow, so we use quadratic Bezier curves defined by the two endpoints and one control point, which is initially located at the axis segment intersection. We use the rank order to move the control points toward the image borders, so that the higher the rank, the higher the deviation and thus the bending of the segment. The use of glyphs also helps in recognizing individual matches. Since we usually visualize up to 50 segments, we just use letters from the English alphabet, which are drawn with the same color as the segment. Let's move to the results. We tested our algorithm using Python. Images had a few million pixels and a few thousand matches. Running times were always below 1 second, including all steps. This figure compares our results with a baseline approach. Here, wrong matches, X, Y, are easy to spot and verify in our output, whereas in the baseline, only X is easy to follow. In this figure, our output shows some outlier matches, for example, P and U, that cannot be checked in the baseline images. This figure shows the benefits of hierarchical clustering. In the context of an interactive application, aggregated segments can be selected to show the underlying individual matches. The same idea with another image pair with an increasing number of uncollapsed segments. See supplemental material for additional results. So to conclude, we have presented a visualization technique for depicting matches between image pairs. We combine hierarchical clustering, layout optimization, high contrast colors, bending, and glyphs to provide images much less cluttered than traditional ones. Those the benefits in terms of visual clarity overcome the loss of information. As future work, we plan to explore transformations beyond translations, considering image contents to optimize the image layout, and the extension to fully interactive and immersive applications. Thanks for your attention.
Great, Carlos. Thanks a lot for a very nice presentation. I hope we are connected well, so you can hear me and I can hear you. So it was very, very nice work. And I'm just checking if I'm starting with some questions from the audience, and obviously I'm not starting with them because there's nothing yet, but guys, be active. So I will start with mine, will be probably pretty naive. But when you are also mentioning at your presentation in the results section that it's quite easy to spot those, let's say, outliers, those lines which are not parallel with the others, and obviously these are errors in the pairing. So could your method be then somehow also used for, let's say, fixing the matching algorithm which is standing behind, or like how this Could you comment on this?
Yeah, well, at least it could be helpful to compare, for example, different strategies and for fine tuning the parameters behind this, behind, for example, the feature descriptors. So actually, identifying outliers is not so easy, because if, for example, for building facades that are clearly visible, usually matches with outlier directions correspond to wrong matches. But many times, because of tree branches and tree leaves and so on, sometimes you get a lot of depth discontinuities, and actually some apparently outlier directions are good matches. Okay, so
yeah. Great, thank you. So I'm checking. Yeah, there's a lot of claps. People are congratulating you. There is a question from Christian Tominski. Maybe I missed it. Can this be applied to compare visualizations or to assist in visual comparison in general?
Well, it really depends on how. So, for example, feature matching between images can be used both for photogrammetry with images which are quite similar and there are small view changes, or for completely different scenes, for example, for motion prediction and for trying to replace some moving objects and so on. So, depending on the view variations, the different clustering strategies can be varied to focus on outliers, or to, for example, evaluate, compare different feature descriptors to check, for example, whether, for example, sometimes we discover when building datasets for building facades that moving objects are really problematic. Okay, and sometimes these might, for example, a vehicle goes to the image. So in this sense, it can assist in this visual comparison.
Okay. Mm-hmm. Perfect, thank you. And we have another question from Thomas Trautner. What would you do if you run out of letters?
Yeah,
for example, if you have more than 26 matches, more letters or symbols would result in more occlusion, I guess.
Okay. Well, we could also actually we use both lowercase and uppercase letters, so and we cycle them exactly the same as the Kelly's palette. Okay, so the idea is only to avoid to help visually tracing the matches for to distinguish from neighboring or crossing matches. Okay, so even with let's say 8 distinct colors and glyphs, usually it's enough to avoid. So you only need to distinguish from potential distractors, which are neighboring arcs and so on.
Okay, perfect. Thank you very much. Looks like from the reaction that Christian is happy with your answer, as we all are, I believe, also with your presentation. Thomas also thanking to you. So thanks a lot once again for your very nice presentation and very nice work. And we are looking forward for some continuation of that.
Thank you.
So with that, we are moving to another paper, which will be presented by Ashok Kumar Patil, and it's about the joint sphere, intuitive and detailed human joint motion representation.
Hello everyone, I am Ashok. I will be presenting our work done at Virtual Environments Lab, Chunggang University, South Korea. Here we introduce a novel motion representation method called the joint sphere. Understanding a delicate human motion in detail from 3D models and image sequences are challenging tasks. A motion can be understood in an image sequence at higher abstractions, but challenging to measure the subtle differences. Therefore, in this paper, we propose a novel motion representation method called the joint sphere. It enables to compare the exact movements of each body joint, which are difficult to understand while viewing an image. And it also makes it possible to understand the meaning of the motion intuitively without viewing an image. In some related work like Yasuda et al., motion belts comprising of key poses are distributed on a time axis and the direction of the pelvis is color coded. This method overlooks joint motion and provides only an overview of the motion without details. Pager et al. Attempted to compare the movement of healthy and injured people by visualizing the quaternion rotation value itself. And in our previous work, we visualized joint rotation on a 3D sphere as well as 2D plane. In these studies, we can recognize the changes in the pattern, but the relationship between the patterns and motion is not so clear. In our work, motion representation using joint sphere, 12 IMU sensors are attached to each limb of the human body, which is hierarchically connected with the parent-child relationship. After calibration, the movement of each joint can be intuitively visualized in the form of trajectory and analyzed in detail by selecting any specified joint in the tool. We attached a joint sphere to each joint of the avatar to visually identify the difference in the joint movements. Each joint sphere represents the range of rotation that the joint can move through 3D space. The contact point will always occur between the surface of the joint sphere and the bones connecting each joint, and these points will change with the movement of the joint. Connecting each contact point and expressing it as a trajectory allows us to identify the direction in which the joint has moved in 3D space. Here we demonstrate joint sphere representation. The video shows the movement of 3 joints in a sequence. The figure shows a right upper arm movement, the brown trajectory on shoulder joint sphere, followed by the lower arm movement, the red trajectory on the elbow joint sphere, and the hand rotation, the purple trajectory on wrist joint sphere. All these trajectories are accumulated in a single sphere as shown here. Although the joint sphere can distinguish most of the movements of each joint, there are some cases where the pattern does not change even when the movement occurs. These cases occurs when the axis of rotational movement is parallel to the bone axis of the joint. Therefore, the rotation is divided into 2 types. First, the twist around the bone axis, that is joint vector, and second, the swing around the arbitrary front vector perpendicular to the joint vector. To track the twist movement of each joint, we used a joint vector parallel to the bone axis and a front vector that points forward as shown in figure. To establish a relationship between the body and the joint sphere, the sphere is divided into 8 parts in the same way as the anatomical plane as shown here. Each of the 8 segments of the sphere, which are 90 degrees apart, is marked with the specific symbols with the starting letters of up, down, left, right, front and back. The beads indicate the orientation of the bone segments. The proposed joint sphere motion representation was evaluated using 3 variants of bicep curl exercises involving changes in the arm swing and twist. The first row shows the end poses of the right arm in the bicep curl exercises and their respective trajectory patterns for each movement in the lower rows. In figure D and E shows the trajectory pattern of arm swinging movement appears to be similar since the 2 vertical movements are similar in action. However, the standard curl has only a vertical swing movement, whereas the rotational curl has both twist and swing of the bone. Thus, we can observe and compare the beads in the patterns in figure D and E, where the filled red area on the beads of a pattern E indicate the approximate twisting angle of the lower arm clockwise by 45 degrees, unlike the absence of filled beads in the pattern D. The white curl in figure C is a variation of the standard curl but differs in the direction of swing. Therefore, comparing the result of 2 motions, the pattern F is located entirely between RF5 and RF6 and the pattern D is located between RF8 and RF9. So we can see that the white curl was performed at an angle of 30 to 40 degrees to the right compared to the standard curl. In figure A, we can observe that the twist angle for the standard and wide bicep curls are constant until the end, whereas the twist angle increases gradually from 0 to 90 degrees in case of the rotational bicep curl. Likewise, the swing results of the 3 variations of bicep curls shown in figure B reveals that the direction of swing in the wide bicep curl is different from the other 2 variations of the bicep curls. A simple dance sequence is visualized on 4 joint spheres. right hand, right foot and left foot. The movement of the left hand is highlighted here as there is more variation in that bone segment. It can be observed that the beads are spread apart when the movement gains speed and closely spaced when the movement is slow, as shown in the right hand joint spear. The overall movement is described using the accumulated 4 joint spears. The representation of human motion using labels provides more details and understanding of any delicate motion. Through our joint spear motion representation method, we can accurately compare complex and similar movements. We can extend our methods by using several spears according to the user's choice. Also, the grid area on the spear defines the meaning of the pattern clearly by a combination of letters and numbers. However, for a prolonged motion, the trajectories overlap. Therefore, it becomes difficult to understand the motion. If this shortcoming can be addressed, then the entire pattern area can be transformed into 2D image, making it easier to reconstruct the motion through image recognition. In conclusion, joint spear, a novel motion representation method, allows for a detailed comparison of each joint using the trajectories. And also, the representation of human motion using labels provides more details and the understanding of any delicate motion. In future work, we will improve the representation method so that temporal order of each pattern can be distinguished and develop an algorithm to reconstruct the movement on 3D avatars that will receive pattern images as input. Thank you.
Great. So I should thank you very much for a very nice presentation. Since we are having you here and I hope we are connected well, right now we are having time for some questions, and actually we are having one from the audience already, and it's from Nuska Smith, and she's asking, anatomically some joints are ball socket hip while some are hinges knee, for example. Do you lose anything by representing all joints as spheres?
We are not losing any data by joining it, representing the data.
Can you try to adjust a bit to the mic because we cannot hear you properly?
Sorry. By representing all, we are not losing any data.
Yeah. So. Yeah. Maybe Nuska can comment if it really answered her question for now. And meanwhile, I also would like to ask about the robustness of the solution with respect to, for example, the length of the movement or the dynamics of the movement, because this tracing on the sphere can is causing some overlaps, of course, at some point, but also it can be quite cluttered at some point. So could you comment on this, how to solve this problem?
Yeah, actually it is our ongoing research work. The overlapping method we are going to trying to tackle with representing the data on the 2D image. So we can, when we take it into the 2D image, flat image, we can, overlapping can be a little bit more, we can understand by taking some keyframes. So then we can tackle that overlapping problem. We are working on it.
Okay, thank you. And Nuska is still clarifying her question. So she meant that in terms of realistic range of motions for the joints, that can be different.
We are using multiple spheres for that purpose. So
you are having different spheres for different types of joints.
Yeah, right. So that joint will, the complete data will be accumulated into a single sphere. So each joint will have its own data. So that will not be going to lose.
Okay. Okay, thank you. Thanks a lot for your answers. And if there's nothing else the audience would like to ask, I think there's, Nuska is thanking you. She's happy with your answer and she understands how you meant it in your solution. Thanks a lot. So we'll be moving to another presentation, which will be given by George Hattab. and it will be about the tool which is called Modeler, and it's a modular and evaluative framework to improve surgical augmented reality visualization.
Today I present Modeler, a modular and evaluative framework to improve surgical augmented reality visualization. The visualization of three-dimensional or 3D biomedical image data in the context of augmented reality often yields a large number and variety of problems. This is especially true when AR is used in surgery. Our main concern is the surgeon's perception. Although occlusion is actually the strongest cue, most of the problems arise due to the small space in which a surgeon operates on. Such problems may arise due to the presence of surgical tools, blood, or even smoke. While AR has a big potential on its own in either being able to enhance or remove visual elements from the scene,
distinguishing different structures and objects of interest within the scene is really crucial. For instance, in the presence of a tumor, blood vessels are risk structures that need to be enhanced. Since surgeons are best suited to understand the data and the underlying structure, I argue that it is crucial to empower the user with parameter selection in either augmenting or hiding such visual information. It's also important to integrate the process of parameter selection within a framework, and to this end, we've created Modelar to render, in the surgeon's perspective, fitting visualizations on the fly. It's important to note that up to now, there is no solution to evaluate and find fitting visualizations for a given task, specifically in surgical AR. Indeed, amid the rising demands for surgical AR systems, the number of applications in the literature has increased drastically, and this occurred across 3 different setups: a head-worn, handheld, and projector camera. Such applications range from the specific domain application of AR, to laparoscopic surgery, to AR simulators, and so on. In general, the Maryland Visual Comfort Scale was developed to measure the perceptual qualities of the visual system. Thanks to the effects of AR on attention, it has been found that designing a viz when AR is active plays a really important role. Although each setup has its own sets of pros and cons, the handheld setup led to most of the problems where brightness and contrast of the object of interest were the hardest to perceive. This is mainly due to the low quality of the augmentation, or the presence of reflections, or even the viewer's angle. To remedy all of that, we've implemented Modelar. It provides actually presets that cover the parameter space of the visual encodings used for an AR visualization. We limit the augmentation to kidney surgery. This means we render 3 objects: a calyx, the tumor, and the kidney surface. Indeed, to accomplish what Modelar is capable of today, we've used graphically a parameter space discretization, so users aren't completely lost in the parameter space, and we render the visualization using Blindfong reflection model, as well as depth peeling methodology to render transparent layers on the fly. Last but not least, we've integrated task-specific evaluation and usability. This was done through the definition of a realistic task, namely contrasting the tumor and the calyx with the visible kidney boundary. This is a common task when the surgeon wants to operate on the kidney to remove the tumor. And different visual channels are integrated: color, opacity, fall-off, depth, and specularity. The screenshot of the graphical user interface, annotated with the 6 different presets that are presented to a user, are helpful. They actually represent from 1 to 4 the combination of different discretized values for each channel, and these how we define them. This design decision permits users to quickly change the viz of each object to solve a specific task. And this screenshot characterizes the first phase of 2, which is the search phase. The refining phase is enabled after imagining that the user has selected a preset that is fitting or subjectively is enough to the needs. And now they move to the second phase, which is refining the parameters to adapt the parameters and the visualization to the different constraints that are provided by the task at hand. Granted, again, this is subjective. This was done in Unity and before in Vuforia. You can see here now we're changing the color, so we set it up in loops. From purple, the surface of the kidney now changes in opacity, and lastly we change the fall-off, so where the boundaries is more or less visible. In terms of results, over 90% of the 24 participants we've recruited had experiences with mobile devices for well over 6 years. However, none of them had much experience with AR applications. They were able to solve a realistic task. This is a screenshot from the previous example. one possible solution, and in terms of presets, 82% of the participants converged to presets 2 and 3, which were the most chosen thanks to the median fall-off that is provided by default. Based on statistics, the overall distribution of the channel usage during the refining phase was identical, yet this phase, which is the refining one, took twice as long as the search phase, which averaged about 100 seconds. This enabled us to identify fitting visualization, at least reducing the parameter space to obtaining a solution space for a specific task. It was also great to be able to record interaction data, such as identifying one participant that took over 6 minutes because they didn't understand the task, totaling twice as many actions, or on the contrary, the fastest participant took 1 minute with exactly 8 actions. Lastly, the usability score was acceptable, recording a 70.5. We think that the separation of the process into 2 phases enabled participants to choose a preset, then refine it for the task, and since participants' preferences converged to similar results in the parameter space, we were able to conclude that modular works and leads to clear results. As you may have noticed, this reduction or restriction on the parameter space may be negative, especially if we are expert users, so we plan to create and add an expert mode. Modular may be used for other legitimate yet typically overlooked questions, such as assessing the perceptual fidelity. Other models may be used for registration, tracking, and augmentation, and this is the modular part of our framework. I'd like to tell you that modular is free to use, easy to deploy, and is adapted for task-based evaluation design. It permitted us to identify presets that best fit the requirements of the task. I thank you for your attention, and I look forward to your questions. Thank you.
Okay, great. Looks like we are back. Sorry for the technical issues, but we have magicians, the backend, who really quickly fixed us. Thanks a lot for that. So we were able to see the whole presentation. It was really nice, George. Congratulations for that. We are having questions, not yet, but people are commenting that it's a really nice work.
Hello.
So I would have a question regarding the study you conducted with the participants. Could you comment a bit more on who were actually the participants, if they were somehow from the domain, or who was that? Thank you.
Of course. Happy to be here, first of all, and thanks for the technical team to support us. So regarding your question, the participants were actually mostly computer scientists, surgeons, as well as professors that were involved. And this was actually, so it comprised mostly during a summer school in the south of France for robotical surgery, participants from that summer school, and also from the university hospital in Dresden.
Mm-hmm. And so what's your plans with the tool, like the ultimate goal of that?
So in general, the tool is, in my opinion, more of a pivotal point. So the community at large is more pushed towards evaluation, to adopting technologies such as augmented reality, and before just getting to, okay, it is cool, but how about we actually look into whether it is actually useful? I hope that this work could be the one of many to come.
Yeah, actually, this is very in line with what I was watching in the morning, the Star section, where Bernhard Prine was presenting his state of the art, and they had very nice discussion afterwards with Stefan Oelze about this actual usability of these tools, and it's very important to get these technologies to the practitioners. So very nice and important work. Thanks a lot for that.
Thank you.
So I don't see any other questions from the audience, and as we had a bit of delay at the very beginning, then we will have to move forward to the next talk. So thanks a lot, George, once again, and having you here. And let's move to another one. The next talk will be presented by Nastasia Steinhauer, and it will be about comprehensive visualization of longitudinal patient data for the dermatological oncological tumor board. So very looking forward.
Hello, my name is Nastasia Steinhauer and I am pleased to welcome you to my presentation of our approach comprehensive visualization of longitudinal patient data for the dermatological oncological tumor board. 3 to 5 minutes decide on the treatment planning and thus on the survival chances of a patient with malignant melanoma, which is the deadliest among skin cancers. Imagine you are an oncological expert in a dermatological oncological tumor board. In these multidisciplinary team meetings, the patient case is introduced orally by a dermatologist, whereupon you and the team have to discuss the suitability of her proposed initial therapy recommendation within 3 to 5 minutes. While patient-related image data are displayed during your discussion, there is no such visual presentation of the clinical data. Thus, you will have to repeatedly inquire or even remember this data from the oral presentation. To support physicians in this concern, we propose a comprehensive visualization of longitudinal patient data during case introduction and discussion. Since patient data is recorded longitudinally, our approach is mainly based on timelines in combination with a cliff-based approach, which was inspired by the visual framework called lifelines. In general, existing approaches visualizing clinical data on the one side support the analysis of longitudinally applied therapies and their effects on a patient's condition, such as CareVis and CareCruiser, which are, however, too complex for the tight tumor board schedule, or on the other side, they focus on providing a comprehensive overview of the current patient's condition tailored to clinical decision-making under time constraints, such as the MOI-based dashboard by Öse and colleagues. In recent years, new drug-based therapies such as immunotherapy and targeted therapy have significantly increased the life expectancy of patients with metastatic melanoma. While some consensus on clinical guidelines could be recently achieved, the final treatment recommendation should consider the individual treatment history, which requires a combined approach from the existing systems, and this combined approach is bundled in our system, which I will briefly demonstrate in the following with the help of an anonymized patient called John Doe. Based on several workshoppings and discussions with the domain experts, we created a user-centric map of information, short MOI, which we have used as a guide to divide our interface into 3 main parts. Patient-specific therapy data at the top, followed by prognostically important patient parameters below and generally important patient data on the right. A legend at the bottom provides a reference for the glyphs used in the interface. During the oral presentation of the patient case, the experts can trace the individual treatment step by looking at the visualization of the therapy data. Thus, we can see that the treatment of John Doe began with a surgery in November 2015, was then followed by an immunotherapy and was then discontinued, perhaps because there was an improvement or no change in the patient's condition. Each treatment step is represented by a glyph with color and shape encoding the UICD established clinical stage of Mr. Doe's cancer, which emphasizes stage changes over time. This redundant encoding further assists when colors are difficult to distinguish, for example when using a projector. So for Mr. Doe, it can be seen that there was a stage shift in December 2018 from stage 2 to stage 4. To explore more detailed information about the patient's condition at a certain point in time, hovering facilities present the respective T&M classification, which results in a clinical stage, and the ECOG stage is a quantification of the general well-being of the patient. Changes in these detailed information are emphasized by horizontal bars above the corresponding treatment step, which are colored according to the NM or ECOG stage, and since the T stage always reflects the tumor size and type at the first physician's consultation, it was neglected here. Immediately after the stage shift, the targeted therapy was initiated where the patient takes a medication on a regular basis, and therefore we added interval primitives having a duration besides instant primitives which show the changes in the medication and its dose. To emphasize therapy is applied multiple times in a month, Gloves with black borders are used, and hovering facilities show all individual treatment applications. The integration of prognostically important patient parameters such as LDH and S100 protein is essential for the identification of newly occurring metastases. And with the help of the line diagrams at the bottom, we can see that these values drastically increase right before the stage shift, but they decrease again right after the targeted therapy was initiated. To assist the experts in finding a treatment recommendation in the current tumor board session, we show the TNM ECOG visualization of the most recent patient condition permanently on the right, which can be compared with an arbitrary previous treatment by selecting the corresponding glyph. Below this comparative view, a list of generally important patient data is shown, which is updated according to the selected treatment step. At the end of the tumor board discussion, the experts conduct a collaborative therapy recommendation in the text field below. We assessed the clinical relevance of our approach in a user study with 5 domain experts regularly attending the tumor board, which was based on real anonymized data of melanoma patients. Due to time restrictions and legal requirements, we decided to conduct our evaluation study outside the tumor board. The resulting questionnaire consists of 8 tasks and 27 questions and is based on the evaluation studies by Forsell and Johansen and by Lam and colleagues. I want to briefly present the results of our study in the following. The left diagram shows the amount of correct answers per task, whereby the partly incorrect determination of critical parameter values in bar 8 can be explained with the coloring of the line diagrams, and the twice incomplete determination of applied therapies in bar 2 with individual learning curves understanding the visual elements. The analysis of 27 questions resulted in these valuable statements, amongst which the following 4 are most important. 4 of the 5 respondents agree that, in contrast to the oral introduction, a better presentation of the data can be achieved using our approach, and 3 of them state that the system requires a low learning and comprehension effort. In addition, 4 experts stated that our approach allows for conclusions to be drawn for the patient's clinical prognosis. These statements already confirm that there is a general agreement regarding the clinical relevance of our approach. Yet it can be optimized through, for example, the integration of image data related information and the history of previous tumor board meetings with their recommendations, which we have illustrated simplified on this slide. Moreover, the integration of the OGG classification could further increase the clinical relevance by indicating also the regression of the tumor. I want to conclude my presentation with the following. Given the current circumstances in the dermatological oncological tumor board, we propose a user-centric MRI-based approach which provides an overview of the current patient's condition and of applied therapies and their effects simultaneously. To assess the clinical relevance of our approach, we have conducted a qualitative evaluation study outside the tumor board, which however has the potential for further evaluations inside the tumor board to assess the time and clinical relevance aspects even more reliably. And with this, I want to thank you for your interest.
Great. Thanks a lot, Nastasia, for very nice work. It really looks very nice, the tool. Let's wait for some questions, if there will be some from the audience, except for clapping and congratulating to you. So I have a question regarding the connection of your tool with the images, because if in Lifelines where you were inspired somehow, we were, as far as I remember, we were able to see also like the image which was connected with the data behind. So is there something which is maybe not relevant in dermatological oncology, or how would you comment on this? Or is it something you would like to add in the future, or?
You mean whether to add the image data into the tool?
Yeah, exactly.
So actually, since the image data is already shown in the tumor board, we really focused on the clinical data. So that was our main goal. show this. However, there was also, like I said in my presentation, there was the suggestions from the experts to integrate at least image-based information, like history of the imaging, and but they did not saw the desire to integrate the image data. However, it could be a nice consideration for future work.
Yeah, but if it's not necessary, then of course it doesn't make sense too much. Thank you.
Yeah.
And I have another question regarding the design, where you were designing your tool. Were you somehow limited with respect to the colors and shapes you used, or you were really like free hand to do whatever you want? I mean, from the expert point of view, they are trained to something there, and you have to stick to it.
We were in a certain way limited that, so we were in close discussion with the experts, and they made a lot of suggestions, and they were also quite enthusiastic about the idea, and had a lot of ideas. So and so we try to be inspired by their suggestions, and and also we use the information shown on the map of information, like we said. So we tried, to stick on this orientation to also to the design, and so mostly it was most important to see the timeline. So that was the main focus to for the design, actually.
Great, thank you. It's always nice to have this excited collaborative efforts, and that they really like your tool. That's great. We are still having one question here from Aditya. First, he congratulates. It's a very nice presentation. And the question is, how are you managing the huge data behind? And is there a way to display the image data in the tool? Yeah.
So since it's a prototype, it's currently not connected to any data. So it was just one patient, example patient. However, we also were thinking about how to integrate it in the system, since it's quite difficult to integrate in the clinical system, since there are a lot of isolated systems. And there's also a lack of interfaces between the systems, or due to legal requirements, it's quite hard to integrate the system. However, since our data is mostly, received the data mostly from the database of the dermatologists, that would be a possibility to connect to this database and then receive the data from this database. But also there are some data, for example, the prognostic parameters that are from a laboratory system, and that is, like I said, a little bit difficult to connect to this system since there are no.
Okay,
what we will consider for future works, definitely.
Sure. Perfect. The second part of the question was about displaying the image data in the tool, and that's something kind of overlaps with my first question, right?
Yeah.
So I think we already managed to answer this. So if there are not any other questions, which I don't see any from the audience. So thanks a lot, Nastia, for a very nice presentation once again, for the answers, and very looking forward for your ongoing research.
Thank you very much. Have a nice day.
So, and we are moving to the next presentation, which will be given by Abhishek Puri, and the topic is Rank Booster. It's a visual analysis of ranking predictions.
In this presentation, we talk about our short paper, Rank Booster, a visual analysis of ranking predictions. We will talk about the background of our work and the motivation for our work, followed by the goals and tasks our system tries to achieve, a description of how our system works, and the current usage of our system as well as the future direction. Now, our work is in the ranking domain, and it aims to help those who are being ranked by a body or authority. As our focus is on university rankings, here is some background information on those sort of systems. First, we have the attributes, which are data points that are collected and submitted by the universities to the body. Then, we have the indicators. Here, the body takes those attributes and combines them in an unknown method to create these normalized values called indicators. Finally, these indicators are combined using a known formula this time to give each university a final score. The relative position of a university's final score will determine their final rank. In this example over here, you can see 3 of the indicators used by the QS ranking body. You can also see the final score, which is a combination of these 3 indicators and others. You can also see the final rank on the left, and you can see this terminology rankee, which refers to the university or entity that is being ranked. Now, our visualization is actually visualizing data from models that are predicting indicator, final score, and final rank values. In our paper, we were given models for each indicator. Now, the way a model would work to be compatible with our system is that it would take a particular set of attribute as input and would then predict what the value of an indicator should be, as well as return a measure of the uncertainty of that prediction. One iteration of this would give us a scenario. So a scenario would be a set of attribute values and the corresponding predicted value and uncertainty measure. Another term is the influence. How much does the predicted value of an indicator change given a change in an attribute? We calculate influence for every attribute indicator pair. So, if we had 5 attributes and each attribute had 4 potential values, we would generate 1,024 scenarios. Now, the motivation for our work is that rankings have become ubiquitous in modern society, and there is real value in having a higher ranking. Studies have shown that higher ranked universities can achieve more private endorsement, more private endowments, and also have access to a potentially higher caliber range of students. And so rankees would like to understand how they can increase their position, both in the short term with regards to the data that they submit, and in the long term. And they would also like to understand how they compare to their competitors. A large body of work has focused on presenting rankings to the end users, but less focus has been given to those being ranked. And so this gives us our focus question. How can we use visualization techniques to help universities efficiently interpret their rankings and analyze the effect of their actions on their ranking? Our work was conducted in collaboration with our university's Office of Institutional Research. It is with them that we created the following goals and tasks. Here we can see that we have 3 different goals. We want to be able to explore the scenarios individually as well as in a group. And finally, we want to be able to compare ourselves to other rival universities. To do this, we created 6 different tasks. We want to be able to visualize a scenario from attribute input all the way up to final rank. We also want to be able to visualize the uncertainty of a scenario's predictions as well as the influence of an attribute on a given indicator. We then want to compare the predictions of multiple scenarios with each other. The last 2 are about visualizing a summary of either the scenarios or the scenarios for multiple rankees. Now we present the video of our system. We start with a blank system. We first select the university that we want to analyze. This is our university. We then look at the list of all attributes and select which ones we want to use in our scenarios. We can also select the range for each attribute. Once we click Submit, we can now see the scenario list view on the right and the global uncertainty view or main view on the left. In the scenario list view, we can see every attribute, indicator, and final variable's value encoded as a vertical bar, with the color telling us whether it's a positive or a negative change. On the left, we can see the main view. Here, we see a distribution for each variable across all the scenarios. For example, in the student ratio indicator variable, we see that there's a lot of variance across all scenarios, with the value for this indicator changing with every scenario. Conversely, for the faculty ratio indicator, it seems all the scenarios seem to predict the same value, at least the same small range of values. And finally, in the student ratio, we see that there are two main peaks for all the scenarios to fall inside. Such insights can be found in this view. We now apply some filtering using this system. Our user wants to explore the high scores, and so selects that specific range. We then go to the student ratio. Here, the user again wants to select the range of scenarios which are in the high range. We now explore a scenario in greater detail. Right-clicking on the scenario allows us to view it in the relationship view. Here we can see the influence, a term that we explain more in our paper, of each attribute on that indicator. Each row corresponds to one scenario, each column to one indicator. For example, over here, each one of those quadrants inside the glyph corresponds to one attribute, with a rectangle on the side of the quadrant telling us the change in that attribute in that scenario. At the top, we have an arc to tell us the current value of that indicator for that scenario. The reason we replicate the information about the attributes is so that the user doesn't have to keep on checking the scenario list view every time. We can also see multiple scenarios in the same view. If we want to look at a scenario in even more detail, we can select it to see it in the form of a radar chart, where each axis shows us the prediction distribution for that scenario for that indicator or final variable. You can also see the values of that scenario shown in the context of all scenarios in the main view via an orange line. We now add a rival university, and here, when we select a scenario now, we're able to see a heat map showing us what is the probability of our selected scenario resulting in a higher indicator or final value score next year, as compared to 3 models which are defined more clearly in our paper. Currently, our system was used during the 2019 data submission by our university to the QS rankings. In terms of future work, we would want to see how we could expand the system to other ranking domains and also tackle the issue of influence between attributes or between indicators. Thank you for listening.
Great. So, Abhishek, thanks a lot for the presentation. And let's check the connection if we can hear, because we had some issues before.
Can you hear me now?
Amazing. Yeah, we can hear you.
That's awesome.
Okay, perfect. So we can have some nice discussion now. So there are still no questions from the audience, but I definitely would like to ask. In your tool, you had quite a lot of, I would call it sophisticated visualizations, which are not very commonly used by regular users, let's say. So my question would be how they were like accustomed to this. What was their feedback? How long did you have to, let's say, train them to understand the visual representations and so on?
So the project actually took over a year from start to finish. And so during that time, we spent the first 3 or 4 months really brainstorming ideas with the users and amongst ourselves to think about the trade-off, like you mentioned, between visual complexity, but also the information that we wanted to present. And so the designs that we use in the paper, we had more complicated designs that just didn't work because the users just found it too visually complex. And we had some more simplistic ones, but they wanted more interactions. They wanted to add more of these layers. So it was an ongoing process after that design phase of 3 or 4 months of kind of deciding what is the optimal amount of complexity. And so it did take around that much time, but by the end, they were able to use it comfortably, and they were able to use it not just with us in a session, but on their own to actually make decisions.
Great.
So that was quite a positive result. Yeah.
Perfect. And can we also use it already? Because it's
we were able to write the paper, but I think actually releasing some of the code that will take a little bit of time, because there's a lot of like checks to go through and to make sure that everything's okay in terms of releasing it, but that's the goal, that eventually we'll be able to just put it on GitHub and have everybody play with it.
Perfect. So let us know when it's available. We will be looking forward to that.
Yeah, same here.
Thank you very much. I think we don't have any other questions from the audience except for clapping, washing hands, and congratulating. So very nice work. Thanks a lot once again for your presentation and your answers. And hope to see you in the future again with some nice presentation of some full paper I did.
Thank you so much. Thank you.
Thank you. And we are moving to the last talk of this session, which will be given by Jonathan Roberts, and it will be about visualizing collocation for close writing.
Hello, welcome to our presentation on visualizing collocation for close writing. In this work, we are presenting the Colocade visualization and text editor tool, especially designed for purpose of close writing. Text analysis is a broad area, ranging from distance reading, collection analysis, to close writing. Our focus is on close writing, with the ability to help people write better. We have been focusing on collocation. These are items that occur more regularly in text. So in visualization, we might say information visualization rather than visual information, or bar chart rather than charted bar or bar plot, and pie chart rather than pie plot. If you want to know more about this, we have a companion paper on multiple views and different meanings and different words. We have used a design study methodology, starting off with design sketches using the 5 design sheets, and then have developed and evaluated the tool as we went along through multiple prototypes, all underpinned by a curated corpus of data. To derive and create the lexical database, we extracted different vocabulary lists and analysed the verbs and complement nouns to arrive at 560 collocation bases, which then we expand into the 30,000 items and examples in the database. This gives us a large set of data that is representative of academic English. We use the 5 design sheets methodology to sketch out different designs and ideas of our prototypes right at the beginning. We then developed a PowerPoint prototype, tested it with users, and then a first prototype, tested it with other users, and then developed the final prototype, which we've been testing with users again. We've experimented and created different visualizations from cascading menus, tree view, an additional more words view, and the double bigram set of words. At every stage of the development, we did an evaluation. So we did an evaluation on the PowerPoint prototype and expert feedback, and we've done evaluations on the prototypes. Initially with 9 participants, and then moving on to a larger 141 study over 5 different sites. So let us start typing some text. This is a quick demonstration of the Colocade editor. Let's try and looking at different words. So let's have an example sentence. Users can edit different words that get automatically highlighted here. And then we can visualize those words in different ways. One of the ways we can do that is through the cascading editor and cascading menu. Let's have an example sentence that we can start to look at. So let's type something like, we design a visualization tool that will demonstrate is acceptable, evidence is clear. So maybe when you're thinking about this, we design a visualization. Maybe there's something about design. Have we designed a good tool? Did we carefully design or originally design the tool? And we can look at different examples of the sentences, and maybe think, well, actually, we carefully designed it. So maybe we can change that to carefully design. So we carefully design. So we have carefully designed a visualization tool that will demonstrate. Maybe think we can, well, how have we demonstrated? Have we demonstrated it experimentally or demonstrated it convincingly, clearly? So we can think about these words. Maybe we've done some tests, we've done lots of tests, so empirically maybe a good way of doing it, or experimentally. So we can add text in there. I'm going to add, we have demonstrated maybe empirically. And then so we can, in that way, we can start to think, well, we've improved the sentence, we've looked at those collocations. Maybe now we can go into another word, think, well, actually, how was it acceptable? Is it acceptable for who? And we can start to look at these different collocations, maybe for the public. So in this way we can see different collocations being pulled up. Maybe have a look a different way. What alternative collocations can we think? So we can look at design, maybe obviously not poorly designed, but potentially cleverly designed. So we can think about some of these. And if we click on the blue arrow, then it will take us to an external database that will give us even more information about that data. Now let's turn our attention to other visualizations. We look at now the tree view. Clicking on different will give us the different words on the right hand side and the collocations for those words. Somewhat different, quite different, etc. We can then highlight, highlighted, and then we can click on those and explore more words down in the tree view. Alternatively, we can look at another view, the double diagram view. So let's click on cases, look at that, and then that has two choices. Pick on case, particular case, and we can see how these words react. Well, thank you very much for listening to my presentation on visualizing collocation for close writing.
Great. So thanks a lot, Jonathan. Very nice work, very nice presentation.
Thank you.
And it's time for questions and sounds of appreciation, obviously, because Aditya is mentioning that it's a very nice tool and wonderful demonstration of that. And the question is if you do have a list of collocations to pull up based on the sentence.
Yeah, so we expand to, we've got about 30,000 words within the database. So not every word, but I think we have, using zip throws, we have sort of a great majority of those words within that collocation database.
Yes, sorry, I'm not sure if it was only my issue, but we were losing a bit at the beginning of your answer.
Oh, sorry.
I'm sorry for that. If you can repeat it once again.
Yes, so we have a careful list, have created a careful list of collocations from looking at bases from academic English. There's a lot of research that's been done to work out what words we normally type and we normally use in different contexts. So yes, we haven't got every word in the database, but we've got a large majority, which expands to 30,000 examples and words.
Perfect, thank you. We are having another question from Carlos Andujar, who is also appreciating very nice talk. And the question is, would it be easy to be able to highlight multiple words to use the tool to simplify or modify collocations? I'm thinking about a use similar to Grammarly, which focuses on simplifying the text.
Yes, I mean, we're trying to do different things, not re-implement Grammarly really, and our focus is on collocations. So the editor will highlight multiple words at the same time. Whatever words are in the dictionary that we have, it will highlight. So yes, it will do the multiple words, but and it will create the examples that we have.
Mm-hmm.
We've got 8 examples for every, or up to 8 for every colocation. So there's a choice that you can do, and some we've got more than 8 examples.
Mm-hmm.
That's what the more button does. So go ahead, click on more, then it'll.
Yeah. Yeah, cool. There is a follow-up question of Aditya still. Are you looking into AI by any chance in your future work?
Yes, in a way, I think AI is definitely where we want to go. We sort of started off with that. In a way, that was our starting point. We want an intelligent tool.
Yeah, sure.
And but yeah, and we're on that journey, and definitely. Visualizations, definitely, we're looking at many different ways to visualize the data and interact with it.
Yeah, very looking forward to that. Actually, I have to admit that immediately when I saw your presentation, when I was checking before the session, I already registered, so I'm in your database and I was checking because I was really curious about that. It's great.
We've checked, and the numbers are increasing. So after today, maybe there'll be even more.
Yeah, I'm sure that it will be
good. Have a try.
increasing.
Not all the visualizations are in the live copy, though, I must admit.
Well, that was one of my questions actually. Is that did you think about some, let's say, visual representations of some? I would appreciate some, let's say, statistical information about how often this collocation is in your database, or how actually this works. So, did you think about some visual encoding of this as well in your tool?
Yeah. So in a way, I think we want to make it simple. We want to make it as a tool to help academic writers. I think adding too many complex visualizations that people are not going to have to learn to use, is not necessarily something that we want to do.
Sure.
But yes, I mean, maybe there's this give us more information. We could have all the statistics information. Yeah, that's a good idea.
Perfect. Thank you very much, and very looking forward. And I will be checking the progress of your tool.
Oh, sure. Thank you. Thanks so much.
Yeah, and Aditya is also wishing you a happy journey. Carlos is thanking for your answer. So yeah, very great work and very nice presentation. Thanks once again. And yeah, so thank you, and hope to see your work in the future again in some way use.
Oh, thanks very much, everyone. Thank you.
Thanks. So, and in our virtual waiting room at Zoom, where it really looked like in a waiting room, we are out of people, so I'm alone there. That means that it concludes this session. Thanks a lot for all the speakers again and for their very nice presentations. I think we had very diverse and very nice combination of topics and the visual representations and algorithms. It was really great. Thanks a lot for the technical support. It was amazing. I really admire what they are doing in the backstage. It's great work. It's a great conference, despite the fact we cannot meet each other and have a couple of beers together in the evening. But yeah, hopefully next time. So thanks a lot for watching, that you were following our session, and enjoy the rest of the conference. And hope to see you again in the future in person. Thank you. Bye.